Okay, we're going to start talking this last segment, talking about how to calculate various effects that solutes have when mixed in solvents. And the first of these is the effect on vapor pressure. And the relevant law is called Raoult's law. And Raoult's law states that the partial pressure exerted by any component of an ideal solution is equal to the vapor pressure of the pure component multiplied by its mole fraction in that solution. And here's the equation. Here is the partial pressure exerted by A is equal to the mole fraction of A times the partial pressure of, or vapor pressure, of the pure substance at that particular temperature. So let's take a look at a problem that it uses this law. This law is actually quite easy to use. And if we read this, it says compute the vapor pressure of an ideal solution containing 92.1 grams of glycerin, and the formula is given there. Molecular weight, by the way, is 92, and ethanol, 184.4 grams of ethanol. Both of these are at 40 degrees. Now, the vapor pressure of pure ethanol at this temperature is 0.7178 atmospheres. And it tells you to disregard the effect of glycerin, that it is essentially not volatile. So let's take a look at how we would go about doing this problem. First of all, I have to open my notebook here. And let me erase this blob that got on here somehow. Okay, so we have to first find the moles of each of these. So we have 92.1 grams of glycerin, and I said the molecular weight of glycerin was 92, and so that essentially gives you 1 mole of glycerin. And we had 184.4 grams of alcohol, ethanol, and the molecular weight of ethanol is 46, and so that is approximately 4 moles. So the total moles, which you need to calculate the mole fraction, is 5 moles. And so the mole fraction of alcohol, which is what you need to know, is going to equal the total moles divided into, which is 5, divided into the moles of alcohol, so that's 0.8. And Raoult's law states that the partial pressure of ethanol is equal to the mole fraction of ethanol times its pure substance partial pressure at this temperature. And if we do the math here, we get 0.142 atmospheres. Alrighty then, so let's move on and look at boiling point elevation. Now the next colligative property that we're talking about here is the boiling point elevation. And the boiling point increases when you dissolve a non-volatile solute in a solvent. And the formula for that is given, the change in boiling point is equal to what's known as the boiling point constant times the molality. Now, when you're doing this calculation, the best way to go about it is to look at something like this. First of all, you have to find the molality of the solution. Once you find the molality of the solution, then using the formula, you find the change in boiling point. Once you find the change in boiling point, you add that to the boiling point of the pure substance, and this gives you the new boiling point. So let's look at a problem. What is the boiling point of antifreeze described in the previous slide, 24, and the kb of water is 0.554. Okay, well let's take a look at that. You can look back, or you can just take my word for it if you remember that the molality that I had calculated was 17.9. And so the change in boiling point is going to equal to kb times the molality, which is going to equal to 0.554 times 17.9, which in this case, if you do the math here, you get 9.92 degrees centigrade. And so the new boiling point is going to equal 100 degrees, because that's the boiling point of water, pure water, plus 9.92, or now it's going to be 109.92 degrees centigrade. Now you can say, let's 110 if you want to look at significant figures here. You have 3 here and 3, and which is your one calculated number. And so if you want to round this to the 3 significant figures, it would be 110 degrees. Okay, if we look at another problem, it says, in this new problem, it says for us to find the boiling point of a solution of iodine that has 92.1 grams of iodine in 800 grams of chloroform. Now, chloroform is the volatile compound, so we need to know the Kb of chloroform and the boiling point for chloroform, and this comes from your book. And the process here is, first of all, you take the mass of the iodine, find the moles of iodine, using that number, find the molality, then the change in boiling point, and then the new boiling point. So let's look at how we do this. First, we have the mass of iodine, which is 92.1 grams. And remember, iodine is one of those diatomic molecules, and so the molar mass of iodine is 2 times the number that's in the periodic table. So it's 253.8. And if you do the math here, you get 0.363 moles of iodine. Now molality, now this is step 2, molality is going to equal this moles divided by the kilograms of solvent. In this case, it was 800, you can't see it here, but it was 800 grams, which is 0.8 kilograms of chloroform. So the molality is going to be 0.454. Then the next step is to take that and the Kb and calculate the change in boiling point. So the change in boiling point is going to equal 3.63, which is Kb, times the molality that we just calculated. And if we do the math here, we get 1.65 degrees centigrade. And then the boiling point of chloroform is 61.26. So the temperature is going, new boiling point is going to be 61.26 plus 1.65. And so now it's going to be 62.91. And to 3 significant figures, it's 62.9 degrees centigrade. So that's your new boiling point. Now these differential boiling points are used in order to separate various liquids from various other liquids, and also to separate liquids from impurities. And this is a experimental diagram showing a distillation process in which what we're trying to do is take a mixed sample and change it into a pure sample strictly using the boiling point. And so you heat this sample up, and the vapor at the temperature that this sample will evaporate, the vapor comes up and goes into this column, and the column then cools it, and then your pure substance comes out in the receiving flask. And this is the way distillation works. Now, because you can't have 55,000 different columns all over the place, they've been able to use differential boiling points in order to stack one on top of another. At each level higher is a higher boiling point. And so what you do is you take the crude, this is called a fractional distillation, and you take the crude oil, which comes in from the left, it enters and it is heated, and then as it gets hotter, each of the various components come off, and the more volatile components rise to the very top, because the highest boiling point is at the bottom, and fuel oil comes out there, and then the next higher boiling point comes out, then the next higher, then the least highest is at the top, and you end up with gasoline, which has a much lower boiling point at the top. And as it says here, at the bottom you get large molecules with high boiling points and low volatility. At the top you get small molecules with low boiling points and very volatile. And this allows you to separate various fractions, and that's why it's called fractional distillation, from a very crude mixture. And this is the way most oil refineries operate. Now the last of the, or no, excuse me, it's not the last. The next colligative property we will talk about is freezing point depression. And as you can see, the formula for freezing point depression is not significantly different from the previous formula for boiling point elevation. The only thing that's different is the constant is a freezing point constant instead of a boiling point constant. And so here, rock salt is frequently mixed with calcium chloride, and these are used to melt ice, and they melt ice by lowering the freezing point so that it becomes liquid at a lower temperature. So a similar problem would be to ask, what is the freezing point of a 0.33 mole solution of a non-volatile, non-electrolytic solution of benzene? The Km for benzene is 5.12 and the freezing point is 5.5 degrees centigrade. And the process would be to take the molality using the first equation, calculate the change in boiling point, and then add that to the standard pure boiling point or freezing point, and you would get the new freezing point. So let's take a look at that process over here. And so it says that we have a 0.33 mole solution. And you remember the equation is that you take that times this Km. And Km here is going to be 5.12. And that's going to give you the change in melting point. And so if you multiply that out, the change in melting point is going to be 1.69 degrees centigrade. So that's the first step. The second step is you now subtract that from the pure melting point. So 5.5 degrees is the pure melting point, and you subtract 1.69, and the new melting point is going to be 3.81 degrees centigrade, and we're at the appropriate significant figure. Now, freezing point depression is commonly exploited to remove, not only to remove ice from the roads, but also to de-ice airplanes, because ice on the wings of airplanes makes it more difficult for planes to fly. And when you do add these different factors, it affects the phase diagram that we've looked at in the past in the following ways. You can see that if the freezing point is depressed, it affects it by lowering it in this dashed line, and if the that's the boiling point is depressed, and if the freezing point is depressed, then it acts over on this part of the diagram. Now the next colligative property, and the last one that we're going to talk about, is the osmotic pressure. And you'll remember from biology that osmosis is the passage of pure solvent through a semi-permeable membrane, in which case you start out with a difference in concentration here. This membrane only allows the passage of the solvent and not the solute, and then as this occurs, more and more molecules end up over here. And osmotic pressure is the amount of force that is required to prevent this from happening. And that can be calculated. So as we said, osmosis is the process of the transfer of this pure solution or pure solvent. And the pressure is the amount of force that you'd have to put on this side to prevent these molecules from coming and diluting and entering the solution. And this can be calculated, and the osmotic pressure is equal to the molarity, which is capital M, times the gas constant times the temperature in centigrade. Molarity, you'll remember, is the moles of the substance per liter of solution. Moles of the substance per liters of solution. So looking at a problem, what is the osmotic pressure of a 3 molar, this is not molality like we've been calculating, this is molarity, 0.3 molar solution of glucose and water that is used in intravenous solutions at 37 degrees centigrade. So let's take a look at how we would do this calculation. First of all, the osmotic pressure is equal to the molarity times the gas constant times the temperature. We said that the molarity is 0.30 times the gas constant, and we'll use this gas constant, and that means that we have to have the temperature in Kelvin, and this is 310 degrees Kelvin, 310.15 degrees Kelvin. If you do the calculation here, you should get 7.6 atmospheres. So the osmotic, if this side is pure water and this side is 0.3 molar glucose, the osmotic pressure here is equivalent to 7.6 atmospheres of pressure. So it's actually quite high pressure. Now this is important in many situations, and just one of these situations is shown in this slide right here. What we have is the effect of osmosis on red blood cells. And red blood cells, as it turns out, are semi-permeable membranes that allow the transfer of water, but not many of the more larger molecules. Now, in any situation, a solution can be hypotonic, isotonic, or hypertonic. Hypotonic means that the concentration of solute is greater inside the cell compared to the solution. Isotonic means that it's the same, and hypertonic means that the concentration of solute is greater inside the cell, greater inside the solution. And so what happens, as you see on the left, is a hypotonic solution, and that means that the solution has less than the cell does, and therefore water passes from the solution into the cell swells and it can rupture. In the middle, everything is cool and the transfer of water is equal in and out. On the right, the solution has more solute than the cell does, and therefore fluid passes out of the cell and causes them to shrivel. So let's say that we have a solution that is 4 grams of a non-electrolyte dissolved in 55 grams of benzene, and it freezes at 2.32 degrees centigrade. What is the molar mass of this compound? And here's what you would have to do. This is how you would work this problem. So let me make this smaller so I can write over here. First of all, you have to see, here's the freezing point right here, okay? So you use that freezing point to find delta F, okay? And in this case, it's benzene, so the original freezing point would be 5.5 degrees centigrade, and the new freezing point is 2.32. So the freezing point depression is 3.16 degrees centigrade. That's this delta F. Using that delta F, you then calculate the molality of the solution. Remember that TF is equal to the molality times Kb, or in this case Km, excuse me. And so that means the molality is going to equal TF, which is 3.18, divided by Km, and in this case that is equal to 5.12. So the molality is now 0.621 mole. The next step is to take that and find the number of moles of the sample. Now you have 55 grams. Remember, molality is equal to the moles divided by the kilograms, and so the number of moles is going to be the molality, which is 0.621, times the number of kilograms, and 55 grams is 0.055 kilograms. And so the number of moles is going to be 0.034 moles. And then once you find the number of moles, you use the mass in order to find the molar mass. So if this many moles weighs 4 grams, if you divide that, this will tell you the molar mass, and the molar mass is 117.1 grams per mole. This is grams and this is moles. And so that's the calculation doing that. Now, one concept that we haven't mentioned yet is the concept of von Hoff's factor. Now, everything that we've talked about up to this point, each gram or each mole has given up one particle, and so it doesn't take into account the possible dissolution of more than one particle per mole. And von Hoff's factor, or I, takes that into account, takes that property into account. So, for example, we talked about dissolving chloroform or iodine and benzene. Well, iodine dissolves, each mole of iodine gives 1 mole of particles. But in this example on the board here, or in the slide, you see that each mole would give up 2 particles, 2 moles of particles, a mole of potassium particles and a mole of chloride particles. And so it has a greater effect on the colligative property. So the ions, when they become more and more separated, they have the effect of being individual particles as opposed to one single molecule. So I'll show you now how that should be taken into account in the next well, not in this problem, but in the next problem that we're going to do. This problem looks at the calculation of osmotic pressure and finding the molecular mass using osmotic pressure. So what we have here is 1/2 liter of an aqueous solution that has 10 grams of hemoglobin, and I measured osmotic pressure of 5.9 torr at 22 degrees. So how do we use that to find the molar mass of hemoglobin? You start with the osmotic pressure. Using the osmotic pressure, you can find the molar concentration. Then subsequently, using the molar concentration, you can find the number of moles, and lastly the molar mass. So let's look at how we would do that on this sheet of paper here. First of all, the osmotic pressure, as I said, was 5.9 torr. Now we're going to have to divide this because the constant we're going to use for R is 760. So that's going to equal the molarity times R times T, so we can use that. We know R and we know T to find M. So if we take this number, which is 5.9 divided by 760, and that gives you this number in atmospheres, and divide that by R, 0.0821, and the temperature, which in this case is 22 degrees, which is 295.15 degrees Kelvin. If we do that calculation, we find the molarity to be 3.2 times 10 to the minus 4 moles per liter. Now the next step, it says, is to find the moles. Well, we have 1/2 liter, so we just multiply this by 0.5 and it gives us the number of moles. So that's going to equal 1.6 times 10 to the minus 4 moles. All I did was multiply that by 0.5 liters, so the liters cancel out. So we have this many moles and it weighs 10 grams. So if we take 10 grams, and that represents 1.6 times 10 to the minus 4 moles, if we do that division there, we get 6.2 times 10 to the minus, or plus, 4 grams per mole. Now let's look at this last problem And this last problem looks at the dissolving of an ion, which will release 2 ions for every molecule. So this takes into account that von Hoff's factor that I was just talking about. So here we start with the mass of sodium chloride, find the moles of sodium chloride, and using the von Hoff factor, we find the number of moles of ions. Using that, we then find the molality, change in freezing point, and the new freezing point. So we're dissolving 4.2 grams of sodium chloride in 125 grams of water. So the mass is 4.2 grams of sodium chloride, and the molecular weight of sodium chloride is 58.5. And so the moles of sodium chloride are 0.072 moles. The next step is to find the moles of ions. Well, each sodium chloride releases 2 ions, so we multiply that by 2. That's a crappy 2, and we get 0.144 moles of ions. And then, using that number, we find the molality. And the molality is the moles of ions divided by the kilograms of solvent, which in this case is 1.25 kilograms. And that gives you a molality of 1.152 mole. And then the next step is to calculate the change in freezing point. And the change in freezing point, delta FP, is going to equal the molality, which is 1.152, times the change in freezing point constant, which, if you look it up, is 1.86. And that is going to be 2.14 degrees centigrade. And then the freezing point of water is 0. Subtract 2.14, and so it's going to be minus 2.14 degrees centigrade. And that will be, let's see, we have 2 significant figures, so it'd be minus 2.1 degrees centigrade would be our answer. Now, I'm sorry that this last segment was long, but I decided just to do that rather than do 4 segments. And thank you for your attention.